Hello, my awesome physics students. I miss you guys a lot. Just checking in. I'm going to give you guys a little run through of the magnetism review sheet. I'm going to go over this so you get a good idea. Okay. What else? Oh, so running out of lessons. We're getting near the end of the year. I have no idea what we're doing probably after June 1st. One of my ideas is revisit units that we previously did. They won't let me do nothing, so I have to do something. Uh, I don't know an adequate way to make a project right now through an online lesson. I don't think it would be very effective. Uh, my thought was going on to a separate unit. So if you guys have time to email me or maybe send me a message in the thing that a unit or a section that you'd either like to revisit A because you liked it a lot and maybe you'd like to go over it again, or maybe you didn't get it so much and you'd like to go over it again. Uh, I'll probably do a whole unit, or with unit one was so big, maybe half that unit or something like that, where we could get through some of it. But ideas that you have, please email me. Hopefully, you can help me determine what the June is going to look like, because I don't really know what June is going to look like. They haven't told me much. Unfortunately, we won't be together. All right, but you have me here. You have me now. This is going to be fun, I think. I hope. Okay, so let's do some physics. Okay, so number one, draw the field lines between these two bar magnets. Now, the important thing to understand with a magnet is that it always goes out of north and into south. So, out of north into south. They never cross. And you get something like this because they don't attract to each other. Remember, north poles are repelling each other. So you have this like blank area, and actually the electromagnetic force here will be 0 newtons. Just so you know, here, right there is 0 newtons. So pretty much what north would look now. If it was north and south, you'd have a different thing. You'd have this was north, and let's say this was south. You'd have them going from one to the other. Know that. That's pretty simple, straightforward. Not a lot of math here. Okay. It's a lot of concepts. So I'm gonna skip the objective. If you guys want to write the objective, it's right there. What two qualities must a particle have in order to produce a magnetic field? In order to produce a magnetic field, you need one. You need a charge. It can be positive or negative. And you have to have a velocity. You have to be moving. A moving charge produces an electric field. So you have an electron and you shoot it somewhere. You fire it that way. It's creating a magnetic field. Which that also means in a wire, if you have a wire and you were having some sort of electrical charge going through it, there's a magnetic field around the wire. Hopefully we learned that already. You saw that in one of our notes. But that's pretty straightforward. I will go over the left-hand rules, which I think is the hardest part of this whole test. Okay, next one. It says, what are the poles of the following bar magnets based on their magnetic field lines? Okay, so remember, out of north into south. It always goes out of north and into south, no matter what the magnet. Even if the magnet is the Earth, okay, which the Earth is a giant bar magnet in a sense. The North Pole, the flux lines are coming out of north and into south. Uh, so the poles of the following, you could just see right here. This is north. They're all coming out. So this has to be a north, and this one also has to be in north. That's why they're repelling each other. When I see this break between them, I don't see them connected. I know they have to be the same. Either it was going to be both south or both north when I first saw the way the pattern goes. And then to determine whether they were north or south, I looked at the arrows. And they're going out of north and back over on the other side. These would track back down into south. That's why we have a compass. That's why we know how compasses work, because it always goes in one direction, out of north into south, and a compass can pick that direction up. Okay, here's a quickie question. Which of the moving charges would not produce a magnetic field? Remember, we needed two things. We needed a velocity, and we need a charge. Okay, so I have moving charges, so they're all moving, so all that. So which one doesn't have a charge? A proton has a positive charge. Neutron has no charge. That's our one. That would not produce an electric field, and our electron has a negative charge. So a neutron would not produce a magnetic field. You could fire a neutron, and there would be no magnetic field. Next one. Now remember, you can pause if I'm going too fast. I kind of thought I went a little fast on that one. What direction is the magnetic force acting upon this wire in a magnetic field? This is a top view. We're looking down on it. Now, here's the trick, okay? For this type of problem, where what direction the force is coming from, okay? This is how we evaluate it. Left-hand rule. Now, most of the time with the left-hand rule, I always say your palm is facing the board, except for this version, okay? The correct answer for this is I put my fingers in the direction of the magnetic field, and it's going from north to south, so my fingers are this way, and my thumb is in the direction of the current. My palm tells me the direction of the force. So if I have my fingers in this direction with the magnetic flux, and have my thumb in this direction, left-hand rule, that means the palm has to be facing up. The palm has to be facing me. So it's pushing up. Now, let's reverse it. Let's say this, say the current was going that way. Now, I put my fingers in the direction of the magnetic field and my thumb in the direction of the current, and now you see it's pushing down, like I'm pushing into the paper. Okay? So that is what they call the third left-hand rule. There's right-hand rules too, which are basically the opposite. You could choose what you want. I'm going to use left-hand rules because that's how I learned and how I always was doing it. But you do have the option for the right-hand rule. Here's another hand rule. What is the direction of current in this wire? Now, for the other two rules, the palm always has to be facing the paper. Okay? So, if I'm doing this, let's see. The current is going in this direction. So it's not, this is the opposite direction. So, in order to do this, I have to put my hand upside down. And then I can curl in the direction of that. And my thumb over here will tell me what direction the current's in. The current is in that direction. Now, that was a really tough example because I had to bend over, because this is my regular hand position, right? But if it's going the other way, I have to turn this way. Put my palm down like that and curl it. It's very hard to show. That way. That way. I'm going to imagine another situation. Let's turn it upside down. Now it's a little bit more doable, right? I could take this, my fingers curl in the direction of the magnetic field, and my thumb tells me what direction the current is in. Okay. So always, palm towards the board, fingers curl in the direction of the current. So you might have to flip your fingers around. Okay? It's a little bit easier to do than to show. Okay. not bad. All right. Same exact idea here. Palm towards the board, towards the paper. Fingers in the direction of the current. So now the current. Remember now, with this type of battery, the current is moving away from negative and towards positive. The electrons traveling along this wire want to get to the positive side. So they're traveling in this direction. Okay? So as they're traveling in this direction, for the second left-hand rule, we change it up. Okay? Still palm towards the board or towards the paper. The fingers are your current, and your thumb is the north. So again, with this one, you see how this is curling. The current is all going in that direction. So I will put my fingers like that, heading down, curling around, and my thumb is in the north direction. Practice this at home. I attached a video yesterday to the left-hand, right-hand rules. Get used to them. They're a pain in the neck. I'll be the first to admit it. And so we said X is the North Pole. Okay. All right. So, still more left-hand, right-hand rules. What is the direction of the magnetic force on the following conductor? The magnetic field is into the page. So the magnetic field is going into the page. The electrons or the current is going in that direction. So if they're going into the page, right, you're going like this. Now, the electric field, magnetic field is going in. My current is going down into the page, current going down. What is the direction of the force? So if you can imagine it the other way, right? If we're looking up at it, right? If this was into the page, and this was out of the page, so if the force is going this way, the electric field is going that way. I have a copper wire, okay, and it has a current that is going that way. So what way would it go? Well, up. Okay, this would tell me up. In this case, into the page, down, it would be pushing it down to this direction. Okay, next one. What is the direction of the magnetic force? One more time. Magnetic force, your fingers go in the direction of magnetic field lines. Your electron is traveling up, so that's like your current. Your electron is traveling in that direction, and your palm tells you which direction the force is. In this case, it's pushing us out of the page. Push, okay? Okay, in order to produce a magnetic field, an electric charge must be stationary. No, that does not produce an electric field. Positive or negative doesn't really matter as long as it has a charge. You can have a negative charge, you can have a positive charge. So, kind of, but not must be, right? It must be moving. Next one. Man, we're going through a lot here. It says draw magnetic flux lines around this magnet with direction indicated. So out of north into south, they never, ever, ever cross. Now you may say to me for a second, well, Lance, before you said that the Earth is a bar magnet, and my compass, if I have a compass, it always points north. Well, that's not because we're not out here. We're on the magnet. If you looked inside the magnet, it would still be going from south to north. You know, it goes the other way. It reverses. So when you're inside on the magnet, it's going from south to north. But outside the magnet, magnetic flux lines are in that direction. Remember, they're not continuous, which means there's always spaces between them. They're actual lines. They're not like, oh, just in that general area. It's not smushed. If you ever took, I wish I still have my stuff on me, I don't, a bar magnet and put iron filings around it, you would clearly see the lines. Okay, out of north into south, never cross. Out of north into south, never cross. That should help you with any time you see those problems. A magnetic field has a flux density of 3.0 times 10 to the negative 2. The wire is 3 meters long and moving at a constant speed of 2 meters per second. What is the EMF induced across the rod? You're killing me. It's not you guys, it's me. I have to go and find the physics reference table. This one, I outsmarted myself. I think that's possible. Let's see, electricity, EMF. We gotta find the formula for this one. Mechanics. Where is this sucker? So basically what the question is, as I'm looking for this, I'm obviously buying time. If I have a wire moving through an electric field, what is the EMF? What is the voltage or current produced in this? That was a it's perpendicular, so I know it works. Why can't I find the right one? Really? We don't have an EMF one? Okay, so we did it. I know it's in there. It's not on the... Strangely enough, it is not on the reference sheet. So let's take the time and find the correct EMF. Okay. Dun, dun, dun. I know I have it somewhere. Go to magnetism. This one caught me off guard. I apologize, guys. Magnetism. But you will have the right answer before we're done here. So, where am I? Light waves. Electricity and magnetism. I'm on the right path. This is actually a very fun unit. If we could have taught it in school. I love circuits. Okay. Let's see, where's the formula for this stuff? They don't give us a formula? Oh, you're killing me. Okay, so now I'm even more frustrated. There's got to be a function here. I'm looking. Left-hand rules. Forces between wires. Come on. Sorry, guys. Magnetism and charges. Here we go. Maybe this is the big one. Where's that formula? Ah. Flux density. Charge. Well, flux density, the wire is 3 meters long. Maybe it's this one. I am very upset with this. Obsessed with myself. I'm gonna give one more page a look here. This is not formula we need here. Let's just look at, maybe it's the generator principle will be enough here. I think it is. Hold on. Here we go. Watch, now I get it. Everyone's like, oh God, maybe he'll just take it off the test. Should, right? So the formula, the voltage, which is what we're looking at, EMF, okay, is the voltage. The B is the magnetic field. The little L is the length of the rod or wire, and V is the velocity. So the EMF produced by a rod or wire going 2 meters a second, perpendicular. It's always got to go perpendicular to the to get anything. You have to go perpendicular to the magnetic field. Is 3.00 times 10 to the negative 2 times length, which is 3, times 2 meters per second. 6 times 3 is 18. Am I right? I'm going to go check my math. I think I am right. I don't know what number it will give me. Maybe it will give me 0.18 volts. Looking at the wrong thing. I need a calculator. Wow, this question took forever. Okay, so 3 second e to the negative 2 times 3 times 2.18. I was right. Or we could say 0.18 volts. That's what EMF is. You know this formula. V equals B times L times V. Okay. Next. Let's try and go a little bit faster here so we can finish off here. Where is the flux density between these two bar magnets the greatest? It's always at the poles. Okay, the flux density is, if you notice, the most lines are right there at the poles, and in this one it's particularly strongest where the two meet. And exit ticket. A charged particle moves through a magnetic field, and the particle is deflected. The magnitude of the magnetic force acting upon the particle is directly proportional to the. Oh my God. So, as a charged particle moves through a magnetic field, the magnitude of the magnetic force, so the other formula we need, which I saw on the other page, which is going to be very interesting. If you guys are patient enough to do this, I will be so impressed. I'm sorry, it's just this video is so long, I don't want to stop it and restart it. Where's my other one? Okay, one more back. Forces between, no. Okay. Our other formula. So. Oh, can you give it that to me? Next one. No, hold on. I'm still trying to find this. This is getting annoying. I just had it before. Third left hand. Out of page. Okay, has to be the next one. Sorry, guys. Wow, this is so much fun. Okay, this has to be it. The force is on the wire. Okay, the force of magnetism equals BQV. Obviously, force. B is the magnetic flux. Q is the charge. And V is the velocity of the particle. Mass of the particle cannot be it. Mass is nowhere in this. Velocity. There's our answer. Velocity. How fast it is moving through the field. Or current, right? How many charges per second, right? Polarity of the magnetic field doesn't have anything in here. The work, there's nothing here for work. Okay, so two formulas. Force mag, okay, the force of magnetism equals the multiplication of the magnetic flux, the charge, and the velocity. And our other formula, I'm going to go back real quick and give you this. Give you this. Where is it? Oh. V, the voltage or the EMF, I'll call it the EMF, equals the flux times the length of wire times the velocity. Again. So magnetic flux and velocity of the charge or the current. Okay. Real quick, I know you guys are probably like, he's got to stop soon. And yeah, I will in a second. Give me a second. This one, I feel like I didn't go over well. Dun, 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 dun. Okay. Here we go. Field lines in. Right? Electron. I saw this. Why am I so confused with this one? Left-hand rule. In and out. So it's going that way. It's traveling to induce it. What way is it going? It's going into the page. I still don't get this one. I'm thinking of something wrong here. into page. I'm going to try and figure it out here. You guys, let's get this right. Of course, if you're slowly doing this, you can see, let's slow down. Page into page, okay. Okay. Let's go back one. I'm looking at the lessons actually online. I'm trying to remember these. Some of these are tricky. Left-hand rolls are not my favorite thing to teach. Carrying wires. Let's see. I'm trying to see if they have a good example here that will explain this to me. Of course, I hope you're looking on the St. Mary's Physics site. Let's see. I'll go with the generator principle here and see how that works. I'm looking at this one problem here. They don't even explain how to do this. All right, flux lines out of north into south. Okay. So you're going, 4 fingers follow flux lines. They're going into the page. Thumb follows movement of wire. Palm push on electrons. Okay, here we go. Figured it out. For this problem. It's going into the page. So my fingers go into direction. Fingers are direction of flux. It's going into the page. My palm is, think of it as pushing the electrons. Okay, so my palm is pushing down. See, my palm is over here, right? And my thumb is in the direction that it's getting pushed. So it's going in that direction. Another I think that's the 4th left-hand rule, as they say. Okay, I don't know. There's so many left-hand rules. Know them for the ones that we did. Okay. All right, guys, have a good one. If you have any questions, just email me. Now I'm giving you a couple of days. You have Wednesday, all Tuesday and Wednesday to test study for this. I'm going to stop this video, otherwise you're going to be here forever. All right, bye.